Alrighty, good people, welcome to the next video. We have done several examples where we've set up the integral to find the area between curves. This time, two things. Number one, we're given no graph, just the equations. But then number two, this is a calculator active problem. So that means we can kind of save ourselves some time. So let's see what this looks like because I have access to my calculator on this problem. Can you sketch the regions enclosed by the following graphs and then find the total area enclosed between the curves? Sketch the region and then find the total area enclosed between the curves. Okay, so I guess I need to graph this and this. So I've already preloaded these into my calculator. I believe I have them in correctly. I do. And so I'm going to go to my grapher. Since I'm using cosine, maybe I'll do a zoom trig. That's going to set up my tick marks to go by, I think it's like pi over 2, pi, 3 pi over 2, 2 pi, and so on. So let me do a zoom trig and just see what it looks like. Okay. So this is what I'm looking for right here. This region that's trapped between these two and this slim region, because otherwise I'm not looking for anything else. So it has to be trapped between those two. Okay, so what do we need to do? Oh, we need to sketch it. So we know what the cosine graph looks like. So this first part, cosine starts at the top, goes to the bottom, goes to the top, goes to the bottom, goes to the top, goes to the bottom. And then this one is going to go through 1, 2, 3. So that's 3 pi over 2. Wait, does it go back? Oh, no. Bunk, bunk, bunk. And then bunk. Okay. So let's go back. Bunk, bunk. So the line goes something like this. Or the curve, I'm sorry. The curve goes something like this. And so we're really talking about this shaded region and this shaded region. So why did they want us to sketch it is the question. They want us to sketch it so that we know which is the top function, which is the bottom function, right? So if I sketch it, I can now see this curve, which is e to the 0.2x minus 2.6. This is f of x, and that's on the top in the first part, and g of x, which is cosine, is on the bottom. But then it switches, and now g of x is on top, and f of x is on the bottom. Do you see that? So I got to be careful the way I set it up. So when I come over here, I'm going to ask myself the two questions that we're supposed to ask, which is, do I know which function is on top and which one's on bottom? I do now. But then the other question is, do I know where they intersect? Do I know where they come together? I don't. All I know is that they are here and here and here, right? And I know that this value right here is the same ending to the first section as it is for the beginning of the second section. So I'm going to take an integral from something to something of f of x. And remember what we said before, if a function is named, you don't have to rewrite the whole equation. You can just write the name of the function. So this is going to be our first integral, this shaded region, right? And then we're going to add it to the second integral. But in the second integral, g of x is the top minus f of x is the bottom. Do you see that? Dx. Let me do that in this color to keep it consistent. So all I need to do is A, find out where they intersect, and then B, use my calculator to set this up. So I went ahead and loaded these in the calculator. I told you, yes, yes, yes. Now we need to find the intersection. How do I find the intersection between here, here, and here? Well, there's a feature called intersection. If you press second trace, option number 5 is the intersection point. Press enter. It's going to ask you a couple of questions. Number one, it's asking you, is this blue curve the first curve that you want to find the intersection for? Well, yes, that's one of the two curves I want to find the intersection. Press enter. And it's going to say, is this the second curve you want to find the intersection for? You say yes, press enter. Do I want to take a guess? I really don't. I guess I could guess that it's close to pi, maybe. I don't know, but just press enter, and it's going to find it for you. So at this point, the x value is 2.674, right? So I'm going to do two things. When I write it down, I'm going to write it up to 4 decimal places because we have to be accurate up to 3. So I'm going to write 4 just to make sure. So 2.674 is what I'm going to write down. 2.674. So my greater, I'm sorry, I didn't put 4 decimal places. I think I missed one value there. 2.6743. Thank you. So my grader knows, hey, I know where the x value is, and I'm accurate to at least 3 places, and I know that because I went an extra one. But here's the nice thing your calculator has. If I get out of there and I come back, oh no, it's gone, right? But your calculator has short-term memory. So if I come back over here and I press X, it's going to remember the last X value it found, which was that intersection point. So here's what we can do. We can store this value in the calculator. If you look at the button right above the on button in the bottom left part, stow, it's actually store. We're going to store this answer that we just got, which is the X value of the intersection point, in one of these green letters. You can choose whichever letter you want. I'm going to use alpha A because it's closest. It's an easy click, click. So I'm going to store this in alpha A. Why am I doing that? Because if I go back to my graph and I press trace and I move this and I come back to here and I press X again, that's not the same number that the calculator remembered the last time, right? It has short-term memory. It's going to remember the last X value that it found. However, because I stored it in A, if I press alpha math, which is alpha A, it does remember it for me. And that's what I'm going to use when I do my integral. Okay, let's go back. I need to find the other intersection points. So I'm going to keep going. Second trace, option number 5, the intersect. Second trace, option number 5. I'm going to move closer to the next intersection point. Again, it's asking me, is the blue curve the first curve? Yes. Is this red one the second curve? Yes. Press enter, and it's going to give me the next intersection point. That is the next intersection point. So I'm going to come over here, press X. There it is. And I'm going to store it in alpha B. That way the calculator remembers this value and it doesn't forget it. And when I write it down, I'm going to put 4.6436, 4.6436, and I'm going to write it over here because this point is where the first shaded region ends and where the second one begins. I just need one more intersection point to find. So I'm going to press second trace. I'm going to put intersect. I'm going to move my cursor closer to the point of intersection I want, which is over here. And it's asking me, is this the first curve? Yes. Second curve? Yes. Want to take a guess? I don't. Just press the enter. And there it is. There's your last intersection point. You could write 6.3959. 6.3959. But I'm going to come over here, press X. There's that number. Let's store it in alpha C. Oh, no. Let's store it in alpha C. Great. Now it's stored. So if I clear everything out, it doesn't matter. My calculator remembers all those values. Let's start setting up our integral, remembering that f of x, the exponential, is going to be the first one minus the cosine, which is the second one. So when I come to my calculator, I'm going to say, hey, calculator, find math 9 from alpha A value to alpha B value of, oh, I had already saved my equations over here, right? So therefore, I can just say alpha trace y1 minus alpha trace y2. I have an extra 2, don't need that, x. This is going to find the first shaded region. But then I'm going to add the next shaded region. So I'm going to do math 9. This time I'm starting at alpha b value, and I'm ending at alpha c value. And my function's flipped. So now I'm going to do the cosine first, which is in y2, minus y1 dx. My buttons. This setup will give me the exact area in between the curves, and that would be 0.80218. So I'm going to round it to 3 decimal places. The final answer should be accurate to 3 decimal places. So 0.802. And that, my good people, 0.802 is the area that's trapped between those two curves and that little sliver, in those two little slivers that are between the two curves. How do we figure this out? We use our calculator to find the intersection points, and we also use the integral in order to figure out the complete accumulation that's in between those two curves. I hope this is making sense in terms of the process. We're going to do some more examples, and we'll do free response questions that are based off of this type of problem.